So again, how do you measure rate? So this is going to be a little less theoretical, and then we're actually going to do kind of a fun example. I do have a lab planned for you, and in a person live lab, but you're going to do it wherever you want. So I'll talk about that in a little bit. It's going to be a home project. So how do we measure rate, right? The way we measure rate is we have to quantify something. So I'm going to have, let's say, concentration 1, right? I'll measure this at time 1. So this is concentration. And again, this is always, time is always what we're measuring against. So let's say it's the initial concentration, and that's usually pretty easy to measure or even to calculate in a lot of instances. We just make the solution so we know the concentration. But oftentimes we measure it, and a lot of times it's using color as the measurement tool. And that's unfortunately what we would have done in lab, but anyways. So you have the concentration at some time, and let's say we'll call that T1, and we'll call that concentration C1. And then in order to get the rate, you need to know how fast the concentration changes. So then you would measure a C2 at a time T2, like that, okay? And this is in fact how you measure any rate. A quantity at one time and a quantity at another time, and then you can calculate rate. So how do I calculate it? Rate, okay, and again, how fast it's going, right, is measured from the concentration change. So where I'm going to do this is the change in concentration over the change in time, like that. Now, whenever we do, oops, okay. Whenever we do delta, right, this is final minus initial. So like remember doing delta H, right? It was always products minus reactions because products is final and reactants is initial. That's why we get delta H. Okay, so it's always products minus reactants, final minus initial. So that means I'm going to go C2, right, minus C1. That's the change over T2 minus T1. And that's how you calculate it. Now, of course, we're going to do it with some data, and I'm going to make it kind of fun. I found this cool video. I don't know if we'll watch the whole thing, but I found this kind of fun video that we can calculate a rate of. Because it was one of those things I didn't know and I wanted to know, right? But I want you to think about this too. Where have you seen this kind of formula before, right? And maybe it's kind of familiar to you. Where you see it is math. Where you see it is a math class. And in a math class, you have a curve that looks like this, let's say, and you want to know the slope, right? Well, probably this is not the best example to use, but let's say the curve looks like this. Then what you're going to do is you're going to go like this. You're going to take 2 points on the line. Now, this line might be actually for some data, but you drew a straight line through it, right? And then what you're going to do is you're going to take x1 and x2 and y1, because that goes with x1 and y2, and then you're going to calculate the slope. And that's going to be delta y over delta x, and that's going to be, right, y2 minus y1 over x2 minus x1. Now, in this case, right, I used x's, but in our example, it was time, right? And in this case, you know that the slope will be negative because the line is going down, and y2, I don't know what I did here. This y2 doesn't belong there. It belongs here. And this is y1. I don't know what I'm on something. I don't know. Yeah. So I was using the point on the corner of the thing I drew. That doesn't count. It's the line. So it's x. It's y, because y2 is below y1. This is where I wanted to go with this. it's a negative slope, because when you subtract those, it'll be negative, and that's why we have negative slopes for the lines that are going downward. Okay? Okay, now, here's the fun one. Hopefully this will work. I'm going to pause the video and save some stuff real quick, and then I'll restart here. You won't see, hopefully, anything bad happen here. So I realized that you weren't able to hear the system sound in those videos, so I'll try and post those for you to see. So here's what we're going to do. We're going to watch a little video, and we're going to calculate the velocity. Okay, so it's like doing a reaction rate, except for velocities are nice because you can see where things are. And this is kind of a fun one. Let's see if I can get this to start. All right, so here we go. So this is a garden slug that you can see right here on the screen, I hope. And we're going to make him move. Now, let's say we want to measure how fast he's going. But, you know, it's a slug. So let me back up a little bit, and let's see if we can start him right at 3 inches. Okay. So let's see where he goes here. So that's at 3, let's say that's at 3 inches, kind of looking right here. At the time is 21.79 seconds. So what I'm going to do is I'm going to go ahead and write that down. I wrote it down, and that's at 3 inches. So he's at 3 inches. So we'll call that 3.0 because I'm pretty sure it's pretty close to being at the 3-inch mark, and it's 21.79 seconds. And now we're going to let him travel. And of course, you know, this is not in real time. This is kind of a recorded video, and then they sped it up. But they go pretty fast. I actually didn't realize they could travel this fast. It's probably heading for my tomatoes or something. I don't know. By the way, they have burrows, and they travel in the same path all the time. So let's say I'm going to stop them right at the 7. There you go. Right a little bit. Yeah, let's call that a little bit past where I wanted to go. Yeah, that's closer. That's closer to 7. Okay, so we're going to call that 7 inches, 7.0 inches. And oftentimes you'll do this on your data. You'll look for spots in your data where it's easy to measure. And that's 2 minutes and, well, 0.96 seconds. Okay, so let's go ahead and go back to our lecture and plug those numbers in. All right, so let's see. How do I have this organized? I have time on the right, and I have x, the distance, on the left. So for time 1, I have 21.79 seconds, and then I have 2 minutes and 0.96 seconds. Okay, and then let's see, what else do we have here? Oh, I have the distances. That's 3.0 and 7.0, and these are in inches. That was an inch ruler. Okay, so we got the numbers we need. So what we're going to do is we're going to calculate the rate of velocity. You would do the same things with concentrations, and then we'll find out how fast the slug goes, because this is one of those things I kind of wanted to know. So what is the equation, right? So the equation would be rate, right, is delta t, or delta x over delta t. That's what I'm dealing with here. And then I'll have 7.0 minus 3.0 inches, right? And then at the bottom, what am I going to put, right? Well, T2 is 2 minutes, so that's 120, right? So again, sorry, my units. These units have to match, just like in any other problem. Units have to match. So I'm going to 120.96 seconds minus 21.79 seconds, like that. And then I can plug it into my handy dandy calculator, which is the calculator I hate, but it's always the one I have on hand. I hate this thing. Oh, so we're going to go 7 minus 3. So if you'll forgive me, I'm not going to use the calculator for that one. That's 4. And then I probably don't need to use the calculator for the other one, but I'm going to, just because I know I'll screw it up. So now it's going to be 120.96 minus 21.79. 21.79. Okay. And then that'll give me 99.17. Okay, so 99 seconds like this. So now I could do the rest of the math. It's going to be 4 divided by 99.17, and that comes out to be, hang on, I got to move these. The controllers for the recording always go to the bottom of the screen, right where I put my hand, and so I've always got to move it out of the way, or I'll shut it off by accident. So, oh, sorry, that's going to be, let's see, 0.0403. And the units are inches per second, like that. And then, the whole sig fig thing, there's only 2 sig figs there, so I'm going to call this 4.0 times 10 to the minus 3 inches per second. It's not really fast, right? They do actually have a race I think it's in England somewhere. It's a snail race, and they put snails on a circular racing track, and they put little helmets on them and everything. It's really cute. Anyways, um, yeah. I probably, just by saying that, have wasted like an hour of your life later. Sorry. Okay, so that's what happened when I did this. I'm like, oh, look at that. And I started watching videos about slugs. All right. So this last segment of rates and reaction rates, I just wanted to give this sort of general formula. You'll see this in your book or something similar to this in your book. I always thought this was sort of the sort of non-intuitive here's an equation and beat yourself up with it approach. But anyways, here's an equation, so beat yourself up with it. The reaction rate for the reactants can be written like this. So what does this mean? If I have a reaction whose coefficient is W, right, and then the reactant is A, to write the reaction rate from that, I would say minus, because it's a reactant, 1 over W, that's the coefficient, times the change for A, or I could do it for B. Now, it's true for the products, right, that I could write 1 over Y for C, because that's its coefficient, and I don't put the negative sign in there, because delta C is already positive. And then I could do the same thing for D. And if I need to solve for, let's say, A from D, all I have to do is set these two equal to each other because these are the same. Okay, so anyways, uh, yeah, I hope that you enjoyed that. So, so that's it for this segment. Next we'll go and we're going to be talking about rate laws, okay?